So let's start simple. I'm sure you've all seen something like this before. I'm just going to make sure that we all are on the same page. So I can write 100 as 10 squared. I can write 1,000 as 10 cubed. So the power, or the exponent of 10, is telling us roughly how big this number is. This works for numbers when we're dividing by powers of 10 as well. So 0.1, which is 1 divided by 10, is 10 to the minus 1. And 0.01 is 1 over 100, which is 10 to the minus 2. And just so that we all agree on this, 1 is the same as 10 to the 0. Okay, and some of these numbers we give special names to. So 10 to the 6 we call a million, 10 to the 9 we call a billion, and 10 to the 12 we call a trillion, and so on. You can carry on naming these. Okay, that's it for boring numbers like powers of 10, but now we're going to look at more interesting numbers. So suppose I've got 240. Well, I can rewrite this as 2.4 times 100, which is 2.4 times 10 to the 2. This is an example of scientific notation. And what that means is that for any number, you rewrite it as a number between 1 and 10 multiplied by a power of 10. And there's two advantages to that one. And the first is that it immediately tells you how big the number is. So in this one, it makes very clear that the number is the same size as 10 to the 2, which is 100. So we think of 240 as being the same size as 100. So its order of magnitude, which is a fancy way of saying its size, is indicated by the power of 10. It works, of course, with smaller numbers like 0.2. It's 2 times 0.1, so it's 2 times 10 to the minus 1. So far, so good. That's the first advantage with this notation. The second is that it makes multiplying these numbers together more straightforward. So, for example, if I want to take the product of these two numbers that we've just seen, I can rewrite this in scientific notation. Now, at this stage, it's just multiplying numbers. There's 4 numbers now. So I can change the order of these numbers, and the answer will be the same. So I can bring together those two coefficients from the front and put the powers together. So 2 times 2.4 is just 4.8. And 10 to the 2 times 10 to the minus 1. Remember the rules with powers, you just add the powers together. So this is 2 plus minus 1, so it's 1. This is 4.8 times 10 to the 1, which is 48. So this is a faster way of reliably multiplying together big numbers. So that's one of the powers of scientific notation, and it's the main toolkit, one of the main things that we'll be using as we go through the session today. Okay, so let's actually start working on some practical problems. So here's our first problem. If we gathered everyone in the world together and asked them to stand in the same place, how much area, what land area would we require? How much space would we have to give them? When I picture this problem, I think of something like this. So we're taking Gru's perspective here, and we're sort of organizing our minions, and we're going to work out exactly how much area we need for these guys. So when I'm answering this question, I think of myself and I think, well, how much area do I need to stand on? And I could imagine myself standing in one of these carpet squares down here, these lovely, lovely carpet squares. So I can think, how much area do I need as one person? Well, this carpet square is about 1/2 meter on each side. So how much area do I need as one person in square meters? Yep. 0.25, it's a quarter because it's a half squared. A half squared is a quarter, so one person, the area needed per person is approximately 0.25 or just a quarter square meters. So I should really write this in scientific notation, but for this straightforward example, I'm going to avoid doing that. Okay, so that's the area per person. Now I just need to know how many people, how many persons there are in the world. Because if I can, the area per person times the number of people gives me the total area. So how many people are there in the world? What's the number of people? A few of you are muttering it. It's 7 billion, right? So this is one of these named numbers. So it's 7 times 10 to the 9. 7 billion people, roughly. Okay. So the total area required is approximately the product of these two numbers. A quarter times 7 times 10 to the 9. Both of these numbers, a quarter and 7 billion, are estimates. So I don't have to be too careful when I do 7 divided by 4. I'm going to call that 2. Don't go back to school and write that. So this is 2 times 10 to the 9 square meters. So that's our answer. So the total area required to get everyone in the world standing together is 2 billion square meters, which is a nice answer, but completely meaningless I can't visualize 2 billion square meters. So the next step is to turn this into something a little bit more realistic, something that we can grasp hold of. So I'm going to convert this square meters answer into square kilometers. So how many square meters are there in a square kilometer? 1,000 almost. So we've got a square that is 1,000 meters on one side and 1,000 meters on the other, because it's a kilometer on each side. So what's the product of these two numbers? Yep, just shout it out. Yeah, 1,000,000. So it's 10 to the 6. So it's 10 to the 6 square meters. 1 square kilometer is 1,000,000 square meters. So this answer, which is in square meters, if I divide it by 10 to the 6, I'll get an answer in square kilometers. So the rules about powers is, if I'm dividing by that one, I'll do 9 minus 6 to get 3. So this is equal to 2 times 10 to the 3 square kilometers. It's 2,000 square kilometers. That's kind of easier to visualize. In fact, we could draw something that has that area. So here's a rectangle. And let's say it's 10 kilometers across the top and 200 kilometers on one side. Not drawn to scale, obviously. So the area of this thing is 2,000 square kilometers. It's 10 by 200. And in fact, I can make this even more easy to grasp. I know that if I'm driving down to Timaru, it takes me about 2 hours, driving at 100 kilometers per hour, so it must be 200 kilometers away. And I know that State Highway 1 is roughly, on average, 10 k's from the beach. So if I make a rectangle with Christchurch in the north, Timaru in the south, State Highway 1 in the west, and the ocean in the east, I've got an area of 2,000 square kilometers, and the entire population of the world could stand together in that area. Does that seem surprising? Yes. Because we're told all the time that there's too many people in the world, there's a problem with overpopulation and so on. And there is, that's true. But the problem is not one of standing room only. So you can now extend this problem, and you can say, well, what if, instead of just giving everyone somewhere to stand, we say, well, we give every family 1,000 square meters to build a house and grow some veggies. That's a bigger area, right? But you could still fit everyone within one state in Australia. So that's still not the problem. We haven't factored in things like generating energy, growing food, producing goods. So all of these things need to be factored in. We haven't factored in the fact that a lot of the world is uninhabitable because it's a desert or a mountain. We haven't factored in the damage that we do to ecosystems when we have lots of people in one place. But this type of analysis forces you to question your assumptions and see what the real problem is. It's not a simplistic one of just too many people in one place. Okay, so we're going to do some work on paper in a minute, so I'm going to start passing these around. Maybe we could just pass them back and people can take them out. So there's a handout coming round. It's got some things on it which I'd ask you not to read. We'll come to them as we go through them. But you can use the back of the paper to make some notes if you want. Okay, so what we just worked on was what's called a Fermi problem, or the Fermi method of analysis, Fermi estimation, something like that. It's named after this guy, Enrico Fermi. He was an Italian-American physicist, great physicist, worth looking up, interesting life, did some great work. You guys ready? He was famous for working with these kinds of problems. So his method is the following. When you want to estimate something, you've got to first of all work out what are your assumptions. Those are the factors and the things that you multiply together. So here are our two assumptions. Here are our two factors that we multiply together. Once we've got those, we need to estimate them. Sometimes we know how big they are. Others we have to estimate. Here we had to estimate the square that I needed to stand on. You'll have more complicated examples. Sometimes you really don't know how to make that estimate. So Fermi came up with a great way of doing this. And he said, first of all, come up with an underestimate. Then come up with an overestimate and put yourself in the middle. It's not quite that simple, though, because if you just take a simple average, you bias yourself towards the big numbers. So if I want to average 1 and 100, I end up being 50.5. It's closer to 100, or it feels like it's more representative of 100. It gets worse if one of the numbers is really big. If I average 1 in a million, I come out at 500,000 something. It feels like it's more representative of a million than it is of 1. So what he said is take the geometric mean. of these two numbers. And all that means is that you multiply them together and take the square root. So the geometric mean of 1 and 100 is the square root of 1 times 100. So it's 10. And 10 is exactly halfway in size between 1, which is 10 to the 0, and 100, which is 10 to the 2. So the exponent is 1. The geometric mean of 1 and a million is the square root of their product, which is 10 to the 3. It's 1,000. Okay? Again, it's more representative of being halfway in size between the smallest and the largest rather than a million. So the second method, and this is on the sheet I just handed out, is you take if you don't know how to estimate something, take the geometric mean of the lower and the upper bound, the under and the over estimate. Then you do what we did here, you multiply everything together, you use a bit of rounding, you use scientific notation. You've got to interpret your answer. You'll get a number like 2 times 10 to the 9. It's a bit meaningless. You put it back in terms of things that you know about. And then, and this is the crucial step, you go back and you question all of your assumptions. Which of those assumptions could I have changed? Which of my answers might be a bit dodgy that influences my final answer? If my answer is different to someone else's, is it because we made different assumptions or because we estimated those numbers differently? It forces you to question your assumptions and check your values of things. So the final step is to refine each step. And that's one of the key things in science in general, is to question your assumptions and check your answers. Okay, so the next question I want us to answer, and actually I'm going to give you about 2 to 3 minutes to work on this yourself, and I'll walk up the sides and you can yell out a question if you've got one. And I want you to talk to your neighbours. Maths is a very social activity. So the question is, how much toilet paper do we get through in New Zealand? I'm talking about legitimate uses of toilet paper, so things like this we're not going to include in the analysis. I love this picture of the cat. Look at its eyes. It's really in the zone. Of course, you can approach this in lots of different ways. I'll give you 2 minutes, and then we'll compare our answers. Huh? What?
You mean like short waves?
Well, I'm leaving that open deliberately. Girls use more than boys? Is there a cat involved? That's probably it. Pulling it off. How are you guys approaching it?
So that's the population.
Yep, roughly. You might need an extra 0 on that. That says 450,000. Close enough.
You know, we use about 5 squares.
Okay, per day? Or? Yep.
We go count once a year.
Okay.
But the year I think the girls
You've got to come up with an average. Yeah. All right, sounds good. Hi.
How many people would you think there are in, what is the population of New Zealand?
It's about 4 million, 4.5 million.
Okay.
So you need a 10 to the 6 there. Yeah, that's it. Start in the toilet. Okay, let's bring it together. I know you probably haven't finished. I'm sorry about that. I'm just very aware of the time. Now, what's normally really good at this stage is to compare our answers and to compare everyone's answers. And that does work really well, but again, we don't quite have time for it. And the reason that that's a good idea is that a lot of you will get a roughly the same answer, but some of you will have quite different answers, which doesn't mean they're wrong. But again, you can go through it bit by bit. You can compare your assumptions to someone else's. You can compare your estimates of those factors to someone else's. And you can whittle down to exactly what it is that's causing you to have different answers. It helps you analyze the problem much more carefully. So this is how I analyzed it. There's lots of different ways to approach it. You can think about how much you use per day, how much a family uses per week, whatever you want. My estimate is going to be that the average person gets through one roll a week. Controversial, possibly. Some of you will use more, some of you will use less. I really don't want to know. So one roll per week, which means I use roughly 50 rolls in a year. So I'm going to get through 50 rolls in 1 year, roughly. I know it's 52, but it's roughly 50. How long is a roll? I don't know. But I do know that it's conveniently subdivided into squares that are about 10 centimeters long. So if I knew how many of those squares I had, I'd know how long the toilet roll was. I don't know how many there are. But a good underestimate would be 100. I'm pretty sure there's more than 100 squares. I'm pretty sure there's less than 1,000. So a good estimate for how many there are would be to use this geometric mean idea and to take the square root of 100 and 1,000. So it's the square root of 10 to the 5. This is roughly 300. Square root of 10,000 is roughly 300. So there's 300 sheets. They're all 0.1 meters long. So one sheet is 30 meters long. So one person uses approximately 50 times 30 meters. This is 1,500 meters in a year. This is, 1.5 kilometers. So each person is using 1.5 kilometers of toilet roll per year. Of course, you could have analyzed how much weight there is, how much volume. I left that deliberately open. Okay, 1.5 kilometers, great. How many people are there in New Zealand? 4 million, roughly. I know it's 4.5. Again, we're estimating. I can call it 4. There's a lot of babies involved. They don't use much toilet paper. So I'll say the total is roughly 4 million times 1.5 kilometers. That's 6 million kilometers. And when you consider that the Earth is 40,000 k's round, this means you can go around, you can wrap the Earth 150 times round with the toilet paper that we use every year just in New Zealand. That is a lot of toilet paper. Where do we grow the trees? How many trees? That would be the next question. How many trees do we need to grow and cut down in order to make that much toilet paper? How much water do we need to pump to feed the factories to do that? How much energy do the factories need for doing that? Right? It starts to make our question about standing room only seem a little bit simplistic, but that's okay. Now we can factor in this area into how much area people need. It's a lot of toilet paper. All right, so there's one more example that I want to get through, and then maybe we can have some questions at the end if we've got them. So this question illustrates something, a really nice principle that I want us to have a go at. The question is how many people are using Facebook right now? The picture is a representation of Facebook, or the friendship network of Facebook. So everybody who's on Facebook is represented by a point, and a line is drawn between two people, between 2 points, if they're friends. So you can see here where there are concentrations of users, and you can see the connections between those users. So New Zealand has got a lot of connections over to the east coast of Australia and up to Fiji and places like that. And you can see Europe and America are quite well lit up. Okay, so this question illustrates a really nice principle, which is a little bit deep, right? It takes a little bit of thought, and it's the following. The fraction of people doing an activity right now is roughly equal to the fraction of time the average person spends doing it. That shut you all up, didn't it? So you've gone very quiet. So that's because this is basically how averages work. If you're averaging over a large number of people, some will use, in this example, some will use Facebook a lot, some will use Facebook a little. Averaging over that, you'll get the same total usage as if everyone used the average amount. Right? So in terms of pictures, what I'm doing is taking a graph that looks like this of different people's usages, I'm averaging it out, and saying I'd get the same total usage if everyone just worked at the average. Right, so a trivial example would be to say we'll spend about a quarter of our time sleeping on average. Right, so a quarter of people, that means a quarter of people are asleep at any one time. Of course, some people sleep more, some people sleep less. That would be the same way to get the same average. Okay, so now we can go back to the Facebook question. So this says the fraction of people doing that activity right now is the same as the fraction of time that we spend using Facebook. So this is a little bit hard. It's going to be quite a wild estimate probably. But we need an underestimate and an overestimate for the amount of time that the average person spends using Facebook. And here we're going to be averaging over the entire population. And there are still some people who don't yet have Facebook, right? So we've got to remember that. So I think a good underestimate would be about 1/4 of an hour. An underestimate for the average amount of time. Right? So I'm not saying that the least amount of time that anyone does is 1/4 of an hour. I'm saying a good underestimate for the average would be 1/4 of an hour. A good overestimate, I reckon, would be 4 hours. I don't think the average is going to be more than 4 hours per day. That sound reasonable? Okay. So a good estimate then, using this Fermi's idea of taking the geometric mean, is to take the square root of 1/4 and 4. Choosing these numbers very well, obviously, because this is 1. All right. So my estimate for an average amount of time the amount of time that the average person spends on Facebook per day is 1 hour. I might be out by a small factor. Maybe it's 50 minutes. It's still close to an hour. So if the average person spends an hour on Facebook per day, they spend 1/24 of their time on Facebook. Right? So this is roughly 1/25. So this is roughly 4%. This is roughly 0.04. 4%, 4 times 10 to the minus 2. So the fraction of time that the average person spends on Facebook is 4 times 10 to the minus 2. That means a fraction of the world's population doing Facebook right now, Facebooking, whatever, right now is 4 times 10 to the minus 2 of the world's population, which we've already seen is 7 billion. So the number of people doing it right now is 4 times 10 to the minus 2 times 7 times 10 to the 9. Okay, 4 times 7 is 30. Obviously, roughly, because everything's an estimate. 10 to the minus 2 and 10 to the 9 is 10 to the 7. It's worrying how long it took for that to sink in for you. It's 10 to the 7. So I'll just tidy this up. This is 3 times 10 to the 8. There are 300 million people using Facebook right now, as an estimate. Now you could question lots of these assumptions. Maybe this is completely wrong. Maybe the average is closer to half an hour. That would change this by a factor of 2. So it'd be 150 million. It's still in the hundreds of millions. You could say, of course it's not completely accurate, because whilst we're awake here in New Zealand, a lot of those areas that were well lit up here are asleep. So probably they're not on Facebook. So there's probably fewer than that right now. But I'm talking about if you pick any moment in time. What's your expectation? How many people do you expect to be online using Facebook right now? And it's in the low hundreds of millions. Okay, so those are the main techniques. We'll have time for a few questions, but I just want to leave you, and they're on your sheets that you've got now, with some challenge questions. And some of these you can just do straight off the bat without any other knowledge than what you've seen here. Some of them, like the question about the fourth one down, if the average temperature of the sea rose by a degree, how much bigger would the sea get? What would the rise in sea level be? You need to know a little bit about thermal expansion of fluids. If Superman or Batman or Spider-Man or whoever you want needs to stop a speeding train, what's the force that they exert? Again, you need to know a little bit of physics to do that, but not much. It's mostly about estimation and the idea of energy. How many people in the world are picking their nose right now? How much energy could we get by flattening the Southern Alps? What would you compare that to? How much energy there is in a can of V? How much energy it takes to launch a rocket? There's other questions like how many civilizations are there in the galaxy? How many molecules from Caesar's last breath are in this room right now? It's not 0. How many molecules in this room were once in Shakespeare's lungs? So there's a few resources there. There's a couple of websites and 2 books and my email address. And my email address is there because I want you to work on these and send me your solutions. I will pick my favorite solution at Friday lunchtime. So Friday noon, I'm going to pick the favorite solution, and there will be a prize which I will send to you for the best solution. And the best doesn't mean that you've answered the hardest question. It means that you've come up with the best solution. And by best, I mean, elegant, and you're comparing it to interesting things, and you're looking at nice extensions.